Hey class, here's our video summary of Chapter 3, Confidence Intervals. We have parameters and we have statistics. Our statistics are estimates of our parameters. Think about having a sample mean is an estimate of the population mean. And I want to know what the average height of all adult males are, so instead I just get a sample, because that's all I can get. But in general, we know our samples are not quite equal to our parameters. There's some error going on there. And so, to be precise, and rather than just claim that our point estimates are the same as the true parameters, it might be better to provide an interval of possible estimates, possible good guesses. So let's make that more precise. For example, according to the CDC, the average height of an adult male in the U.S. is 70 inches with a standard deviation of 5 inches. Now, that's not entirely correct. What they're really saying is out of all the thousands of people they sampled, the average from that sample was 70 inches with a standard deviation of 5 inches. So, a more accurate statement would be the CDC is 95% sure the average height of an adult male is between 60 and 80 inches. I use the 95% rule. We'll talk about why that's justified later. So again, instead of saying the average height of adult males is 70 inches, which might be true, but it probably isn't, a more accurate statement would be that we're 95% sure that it's between 60 and 80 inches. Okay, again, we lose precision there because instead of giving a single number, I'm giving an interval. But this way, at least, I'm saying a true statement and not something that is potentially factually incorrect. Other parts of Chapter 3 to keep note of, we'll be doing more computing using Statkey, reading off descriptive statistics, and various forms of bootstrapping, which we'll talk about, you'll see in Section 3.3. Section 3.1 is sampling distributions. The big thing here, I think everything will just fall in place if you understand, well, what a sampling distribution is. So recall, a distribution is not only the possible outcomes, but the probabilities of each outcome. That is, what can happen, how often it can happen. Here's the definition. You can read that on your own. But I always think about it in this scenario. A sampling distribution is like this. Suppose you had 100 people, say 100 students, 100 researchers, or something like that, and you want to know if everybody in the town supports something. Say, if they support raising taxes to renovate a park. Some people might be okay with this, some people might not, and us 100 researchers want to know. All 100 of us go out and sample 1,000 people. Well, that means some people may get sampled multiple times. They may get asked the same question by another person. But we're going to sample 1,000 people. All of us will do this. All of us will compute our sample proportion. When I ran this experiment, 52% of the people supported renovating the park. When somebody else ran this experiment, 53% said they supported the park. When somebody else ran the experiment, somebody got 50% supporting the park, and so on. We're all going to get different numbers. Presumably, if we if our sampling was done in a sufficiently random way, all our numbers will be kind of close, but we're going to get a wide variety of numbers. And if we graphed all of them, that would give us a sense of what the distribution of possible outcomes is. And that's what a sampling distribution is. We imagine what all possible samples could look like. I might accidentally ask 1,000 people, and all 1,000 of them say they like the park, or they support the tax increase for the park. Or I might ask 1,000 people, and I might get none of them. All those things are possible. It's just some values are more likely than others. And that's what the sampling distribution will help us understand. Again, if that's a little bit confusing, that is fine right now as you work through problems, as you give this time to kind of soak in. I promise you it will make sense, but if you really, really feel uncomfortable about this, especially after doing the homework, please let me know, and I'm more than happy to give some more supporting material. But that's a sampling distribution. Section 3.2, understanding and interpreting confidence intervals. So now we're getting more into the nuts and bolts of what a confidence interval is. The thing I want to emphasize here is on page 187 there are these list of, I believe, 3 different misinterpretations of what is a confidence interval. Please look through them. Try to think about which one that makes the least sense to you. Let me know if you're having trouble with this. Confidence intervals are a little bit weird, especially with these sort of bootstrapping methods, and so let me know if it isn't working out. Section 3.3 is actually how we compute bootstrap confidence intervals. I like to think about kind of how to explain this to other people. Well, bootstrapping. So as you're learning this stuff, think about how you would explain bootstrapping to others. We're going to be using Statkey to do this, to generate our confidence intervals. And you think about the phrase pulling yourself up by your bootstraps. That's kind of the philosophy in bootstrapping. I do have a YouTube video you can watch that shows you how to do this in Statkey, so look out for that. 3.4, that's the last section in the chapter. This should be the point where everything kind of pulls together. If you still feel completely lost at 3.4, then do let me know. I'm more than happy to go through these things again. And alright, well, that's all I have for chapter 3, and I'll talk to you soon.